So today I'm going to depart from what I've been talking about, that is the kinetic theory, and focus on another problem that is under the broader heading of micromechanics, and that is to attempt to understand the quasi-static, that is slow, elasto-frictional behavior of an aggregate, a random aggregate of identical spheres. So this is a problem of the statics of granular materials, if you like. And first let me say that the philosophy of the activity is the same. That is, first we characterize the interaction between a pair of particles, and then we carry out some appropriate averaging scheme in order to scale up to the continuum level in order to have a continuum formulations for implementing into existing continuum codes. It is also possible to do what is called, in this subject, discrete element numerical simulations, the analog of what John does with Stokesian dynamics, and consider the interaction of large numbers of particles with one another, and to measure from those simulations the various quantities here that we are going to be attempting to predict. And in my view, these are complementary activities. The modeling activity can inform the simulation in terms of how to interrogate the simulation, and simulation provides a test for the modeling activities. So I'm interested in deriving stress-strain relationships and the moduli that appear in them. And an important element in the mechanics of granular materials of this type, that is contacting granular materials, is that shearing is typically associated with expansion of the material. So we'd like to say something about that, predict it to the extent we can. There is typically inelasticity exhibited by a deformed aggregate, and we'd like to characterize that inelasticity. And also there's a failure of a typical granular material through a process of strain localization. So let's suppose we have a typical sample of a granular material. It's often enclosed in a membrane and surrounded by a liquid, so that pressure forces can be exerted on the material. And let's say we load it axially, if we like, maintaining the pressure constant. And what I mean by failure through localization is the means by which this column will deform for a while homogeneously, and then the failure will involve a band of, or one or more bands of rapidly sheared material, a band in which the shear strain is localized. Okay, it'll be interesting to predict that type of failure. Now, I'm not going to do all of that today, but I'll indicate for you the simplest theory that we can employ to describe this aggregate, and show you what we can predict from that. And then I'll say something about how this theory fails, and then I'll try to go a little bit beyond that theory in order to make more faithful predictions of what's observed in experiments and numerical simulations. Okay, so the simplest theory is based on something that I call the average strain assumption, but is very common in various areas of solid mechanics. In physics, it's sometimes referred to the Born assumption. And the idea is that there is an average strain associated with the loading of the material, And the assumption that you make about how typical particles are displaced as they participate in this average straining is that you assume that the deformation experienced by, let's say, the line of centers or the line from the center of particle to the contact is determined by the average strain. Okay, well that's easy to do. We know what the average strain is, and once we have the let's say the component of deformation along the line of centers, the component of deformation of the centers or the points of contact tangential to the line of centers, we can calculate what the force is between the particles and do our averaging. Okay, so that's what I'm going to do in the very first theory, and from that we can generate a lot of information. Okay, so here's what I'll do. Analytic expression, volume change, stress strain, plastic strain, strain. Well, I don't know if I'm going to be dealing with strain hardening. I won't be talking about the plastic behavior much, although I'll indicate what its origin is and perhaps say something about contact evolution. Okay, and let's see. And these, I say that an advantage of the micromechanical approach is that these expressions are going to be couched in terms of the particle diameter, the properties of the particle surface, and one parameter that is perhaps unique to granular materials is the average number of contacts per particle. Okay, and finally the volume fraction. Now, what I mean by the average number of contacts per particle being unique to a granular material is at a given volume fraction, an aggregate of granular materials can be prepared in such a way that there are different average numbers of contacts per particle. And that influences the behavior of the granular material. And that's a unique property of a granular material, if you like. And this average number of contacts per particle in the language of the subject is called the coordination number. So I'll refer to it as the coordination number. Pardon me? Monotone loading? Is that what you said? Yeah. Oh, it means that the loading is not reversed, one direction. Okay. If to see real evidence of the plastic behavior of the material, you want to load and then unload, and you see that that's doesn't result in a reversible stress path. Okay. So I'm just going to be talking about loading. Okay, well, here's a picture again, and introduces a little bit of notation. So I'm going to be calling the compressive strains, denoting the compressive strains by capital letters. I'm going to be focusing on an experiment, let's say, in which the pressure is kept constant. This is a common experiment. You have your granular material enclosed in a membrane. You put it in a liquid in a testing device, and you can control the pressure then of the liquid that you're compressing the grains with, and then you can further strain the material. And typically what you see is, so Q is going to be the deviatoric stress, and P is going to be the pressure, gamma is going to be the shear strain, and capital theta is going to be the volume strain. And the typical experiment that one sees in carrying this out is maybe an initial linear part of the stress ratio versus the normalized strain. And I should say this volume strain, subscript 0, is the volume strain associated with the pressure you're confining it by. So a granular material responds differently depending upon how much you're squeezing it together. Okay, so in that way it also is somewhat unusual as a solid body. So it's a natural, this volume strain, measure of strain, is a natural strain to normalize the subsequent shear strains that you subject the body to. And then associated with this straining is a change in volume. So capital theta prime is the change in volume from the initial volume. And there's an expansion. And because I'm measuring strains, positive being compressive, that expansion is regarded as being negative. So we'd like to say something. We'd like to say something about this behavior from this assumption of the average strain dictating the kinematics of the interaction between.
What was theta prime?
That's just the additional, yeah, the additional volume change.
Because you're shear.
Yeah, exactly. And in this experiment, we're not shearing with rotation. We're shearing because we have a deviatoric that is the one component of the stress is different from the other two components of the stress. And we're axisymmetric, of course. So that simplifies the situation that we're dealing with. So now I'm introducing some notation. So the volume strain, as I said, is indicated by theta. The shear strain indicated by gamma. These are related to the strains, to the average strains applied to the sample. And the average strains, of course, are measured just from the average motions. So this notation will appear. I'm denoting the orientation between two contacts with a unit vector. So here's a unit vector, and I guess let's see. So what is my polar angle here? It looks like the polar angle I'm denoting by theta, and the circumferential angle I'm denoting by phi. Okay, that's fine. So here is the average strain assumption. It relates, in this instance, it relates the displacement of this point relative to the center in terms of the average strain, which is known unit vector that indicates the orientation of the contact that we're interested in. Okay, so there the kinematics is finished. We can look at the component of this along the line of centers, and that's what I call the normal component. Maybe that's not the best nomenclature, but it's normal to the plane of intersection. And let's see. And the normal component of displacement can be written in terms of the volume strain, the shear strain, and the polar angle. Okay, so this is all kinematics. The tangential component of this displacement, you project this along a vector perpendicular to D, that is projected along this vector, unit vector. And you can determine the tangential component of the displacement of the contact in terms of the average shear strain, the diameter of the particle, and the polar angle. Okay, so I say this is just geometry based upon this assumption. So we know how every contact in the aggregate is going to deform, as long as we know its orientation. And now let's say something about the contact force. So the contact force has a component along the line of centers and a component perpendicular to the line of centers. And the normal component is given in terms of the normal displacement by a Hertzian contact law. So we're making use of Hertz analysis of contact between spheres in order to relate the deformation along the line of centers of the spheres to the normal force required to maintain that deformation, and that is an inherently nonlinear relationship. Okay? It's nonlinear because the geometry of the spheres play a role in determining that relationship. And there's a coefficient that appears in that relationship that's related to the shear modulus of the material of the spheres. So if we have glass spheres, we know what that modulus is. And nu, I beg your pardon, so to conform with tradition, I'm going to have to let nu here denote the Poisson ratio of the material of the spheres. Okay, so here are the properties, these two parameters then are the property of the material of the spheres. Okay, and let's see. So that's the normal component of the force. And I say we know it now because we've related delta to the average strain. And the tangential component, there are two kind of pieces of the response of the tangential component. If the tangential force is less than a factor, which we identify with the coefficient of friction of the coefficient of friction at the contact, then there's an elastic response of the contact. That is, we can, provided that the tangential part of the force is not too great, the contact's not going to slip. It's just going to deform elastically. So there's that possibility of elastic deformation in the tangential direction in the contact. But if that tangential force, if this guy gets too big, then it's limited to be a coefficient of friction times the normal force. Then it's sliding, okay? And maybe getting a little bit ahead of ourselves. So that sliding is one element of the inelastic behavior of the aggregate. That is, the contacts themselves are not behaving in a purely elastic way. They're sliding, and when we reverse the stress, if we focus attention on a simple contact, reverse the stress, that contact's not going to slide back initially. First, it's going to relax elastically, and then it may slide, but perhaps not all the way back. Okay? So, I mean, this so simple an analysis does give us some insight into what's happening within the granular material. And this elastic modulus is well characterized, again, by the shear modulus, the Poisson ratio, and it depends also upon the normal displacement, the displacement along the center line of the contact. Okay, so now I introduce some more notation. I'm sorry, but so I'm going to call little b essentially it's a combination of the volume strain and the shear strain, and c is just a numerical factor times the shear strain. And what I'm interested in doing is characterizing contact slip. So here's the axis of symmetry. Here is a typical particle. Here's a typical particle in the aggregate, and I'm going to be talking about its contacts with possible neighbors. So depending upon the orientation of contacts, and given the straining that this aggregate is experiencing, what we see, or what we can characterize. I'm not going through the details of the calculation, but we can characterize the orientation of the contact that will first begin to slide. Okay, so that's an interesting quantity to characterize, and and the calculation is not really very mysterious. You just plug in the expressions for the forces and determine the angles at which the tangential force first equals mu times the normal force, and that gives rise to a characteristic angle of first sliding, and everything about that angle then is known in terms of the coefficient of friction and Poisson's ratio. Okay, so here's an example. And I should say, there's some ambiguity. So the question is, what coefficient of friction do we use? Do we use the static coefficient, or do we use the sliding coefficient? Okay, numerical simulations indicate that it's the static coefficient that is the one that should be employed. Okay, so let's see. So that says when sliding is first possible, and so this is the angle theta c, the angle which sliding is first possible, and then we continue the calculation and we can find the largest polar angle and the smallest polar angle for which contacts have slid. Now, I'm doing everything in this quadrant here, but everything I say in this quadrant is reflected into this quadrant, and this quadrant, and this quadrant, okay, because of the symmetry of the problem. Okay, so this is telling us that continued shearing will give rise to a region on the shoulder of a typical particle, right shoulder, left shoulder, bottom left shoulder, bottom right shoulder, in which particles are sliding, in which their tangential force is limited by their normal force. Okay. And we're involved in this because we're going to use this information when we average up to calculate the stress. So we need to know how our contacts are behaving in order to integrate over the full range of contact orientations in order to get the stress. Okay, so that's fine. And then what happens is, as the shearing continues, so now I'm imagining the shearing continues, what happens is the region of sliding contacts grows until the greater angle is 90 degrees. Okay? Now the lesser angle never goes to 0 degrees because the normal forces in the area of the pole are dominant, they're strong. Okay, because we're loading that way. All right, so that's fine. So what happens after slip has advanced to 90 degrees, and what happens then is contact begin to be deleted in that the force of contact goes from compressive to tension. And of course, these contacts can't sustain tension. So we assume that the contact is deleted at that point. Okay, so there's the story. There's the story of contacts that result from this average strain assumption and realistic models of how contacts are interacting. Okay, so I introduce this angle theta 1. Well, so then this theta 1 then would be the extent of contact deletion. And you might say, well, how can the material stay together? Okay, so now let's talk. So now we've got the story of the contacts. So now let's talk about how we go about calculating the stress. So we take a formula for the stress that was first introduced by Cauchy in his study of solids. In fact, the way that Cauchy modeled what he thought was a characteristic solid was as a granular aggregate. And the way that he first calculated the stress was based on contact between grains of a solid. Although he knew nothing about molecules or atoms, but he apparently thought that was a plausible analog. So the expression for the stress involves the number of spheres per unit volume, their diameter, the contact force, the unit vector to the contact, and something called the contact distribution. So the way we're going to characterize the statistics of the body or of the aggregate is to say something about how contacts are distributed. So how might they be distributed? Maybe I'll just work in the first quadrant. So we might have contacts distributed more along the pole than along the equator. That seems natural. Maybe you'll be bringing contacts or bringing particles into contact by deforming them, or what I've just said is that there's a possibility of contact deletion. So perhaps something like this is more likely. Or let's say, so from this point on. And initially, I guess if we isotropically compress this aggregate, we can imagine that the distribution of contacts is isotropic, and then the integral over this distribution is always going to be related to the average number of contacts per particle. So K is the coordination number. And this, the 4 pi here is just so that integrating A over a solid angle or over the unit sphere gives the average number of contacts per particle. Okay, what else? Oh, and here, then the volume, so now I'm denoting the volume fraction by V. And that's what we were really more accustomed to than the number density. And the relationship between the volume fraction and the number density involves the volume of a single sphere. So that's a relatively easy relation. And when we use when we introduce I'm going to assume that I can make use of an isotropic, at least initial distribution, and then the expression for the stress is given in terms of coordination number, volume fraction, particle diameter, and the normal and tangential components of the contact force, and this is integrated then over solid angle.
So the definition of stress that the computation of stress that you do is precisely what they do in discrete simulations also.
Yes. Yeah. Okay, so now let's see. So I'm going to use this expression for the stress. And the first thing I'm going to calculate, let's see, so here's the expression for the stress here. So the first thing I'm going to calculate is the pressure.
Sorry, what was A of B? Fabric tensor.
Yes, that's what it's often called, yes.
So it's the isotropy of the way contacts are distributed.
Well, no, fabric tensor is the second moment of, this is simply the distribution of contacts. It can be, if you like, expanded in terms of its moments, and then the second moment is the fabric tensor. Okay, so let's calculate volume change. Based on that expression for the stress. So the definition of the pressure is 1/3 the trace, the sum of the diagonal elements of the stress. If we take the sum of the diagonal elements of the stress, only the normal component of the contact force enters. The normal component of the contact force we had expressions for in terms of delta. So I'm simply making use of the relationship that we had earlier. These relationships. And what results is a relationship between the pressure and measures of the volume strain and the shear strain. I'll remind you what the definitions of B and C were. So this is a combination of volume strain and shear strain. This is the shear strain itself. Okay, and this is an integral that can be carried out. We integrate over, well, we're symmetric in phi, so we need only integrate over theta. And here then is an explicit relationship between the shear strain, the volume strain, and an initial volume strain that is associated with the pressure and the, if you like, the elastic response of a contact. So this is, let's say, a goal of our study. We'd like to understand how changes in volume accompany shearing. And I should say that so we've assumed that the contact distribution is isotropic, but in carrying out this integral, we're careful to integrate only contacts that exist. The upper limit of the integration is the angle at which contacts are deleted. Okay, so if you like, anisotropy is entering the problem through contact deletion in this simple calculation. Okay, and also, so here was, I remember I referred to theta 0 when I was showing you the graphs of typical behavior. So this is the measure of volume strain that is associated purely with the pressure. And that serves to normalize all the strains in this relationship. And for example, here's a prediction. So here's a prediction of the strain versus the normalized shearing, and that rather complicated expression that I just wrote down then it provides this relationship over a reasonable range of normalized shear strain. Also, here is a figure that shows what I was attempting to illustrate here about how particles begin to slip, how particles begin to delete. For example, slip starts at about a little bit greater than 50. No, well, for a while it's just pure, everything's purely elastic. And then slip begins to spread towards the equator as the shearing continues. Slip begins to spread towards the pole as shearing continues. And then at a value of the normalized shear strain that we can calculate, the slip has reached the equator, and then deletion begins to creep towards the pole. Okay, so that contains the information about the contact behavior. Shear stress, more complicated. But we can calculate it. That is, so we divide the shear stress into two pieces, two contributions. One is the contribution of the normal force, and the other is the contribution of the tangential force. And I say we can calculate these contributions. When we calculate them, we're careful in calculating the contribution of the normal force to integrate only to the point where contacts are being deleted. When we calculate the coefficient of the tangential force, we do that in one of the integrals involving the elastic response, the tangential elastic response, and in the part of the contribution from the slip region, we use the angles that we've calculated that bound the slip region. Okay, so in that way, we're taking into account the details of what's happening at contacts that are variously oriented. And here's what we get. So we're predicting now the shear stress. So this is the ratio of Q over P, and this is the ratio of gamma over capital theta 0. And the normal contribution, coming principally from the anisotropy of the loading and orientational distribution, is this. The tangential, initially elastic, and then stays pretty constant as particles slip. Okay, well, let's say it seems like we're doing great here. Now the question is, what's the quantitative comparison of what we predicted to what's observed in numerical simulations and experiments? Okay, and here's the story. That what we just predicted is what? 3 times what's observed in experiments, and perhaps 4 times what's observed in numerical simulations. Okay, in other words, we've made some wonderful predictions, but the predictions are indicating that the material, the theoretical material, is behaving far too stiffly. Okay, and that's the problem with the average strain assumption. That is, we're dictating how the individual pairs of particles are moving. We give no consideration to force and moment equilibrium. And force and moment equilibrium are acting to equilibrate every particle in this aggregate because the aggregate's random, I should say. If the aggregate were periodic, the average strain assumption would be working well. But because the aggregate we're dealing with is random, we're not taking into account the equilibration that's necessary to get a realistic behavior of the material. Okay?
Equilibration of the single particle.
Every particle, let's say, every particle seeks and achieves its own force and moment equilibrium. Okay, so the answer is, well, I mean, this is interesting to have done it, but if we want to have quantitative comparisons with the simulations and experiments, we've got to do something more. All right, so now I'm going to, yeah.
You're saying the particle is not in equilibrium?
Well, there's no consideration of equilibrium in the average strain analysis. Yeah, so in general, individual particles are neither in force nor moment equilibrium.
But in the analysis you have done, it will be in equilibrium because of symmetry.
No, not the individual particles.
Because you have got a shear and everything is distributed nicely.
No, individual particles are interacting with different neighbors and with.
You have got isotropic distribution. And
That's the continuous distribution, if you like. But in the real aggregate,
no, not in the real aggregate. I am saying that the computation that you have done is self-consistent.
is what?
The computation you have done is self-consistent in terms of.
Oh, yeah, it's self-consistent, but it's just not quantitatively correct.
That's because the real aggregate it is not isotropically distributed, or the contacts may not just be symmetrical.
Yeah, that's right. That's right, exactly. Yeah. Yeah, but so I want to be able to say something more about the real aggregate, okay?
Jim, is that like a fine deformation on each
Yeah,
part?
yes, exactly.
There's no reason they have to be all fine. That's
Right. Okay, is it clear? So that what I call the average strain assumption, or affine assumption, or Born's assumption is wonderful, and that it allowed all these calculations to be made. And I think the calculations are interesting and maybe improve our understanding of the micromechanics of granular materials, but quantitatively, no. Okay, so now I want to indicate as briefly as I can maybe a first step towards advancing beyond the average strain assumption. So I want to introduce now deviations from the average strain assumption. So that's what I'd call fluctuations here. And I'm going to use force balance, moment balance to determine deviations from the average strain assumption. And I'm going to try to introduce a more realistic description of the local packing, and that'll lead me to averaging. Okay? So what I'm going to do for a typical pair of contacting particles with some orientation, an arbitrary orientation relative to the polar axis, I'm going to imagine that they interact with one another in a way that's different from the way they interact with their neighbors. I'm going to suppose that these particles have translational and rotational degrees of freedom that are going to be determined by force and moment equilibrium on each particle, assuming that their neighbors are moving with the average strain. That their neighbors move affinely, but they are going to be showing fluctuations that we determine from force and moment equilibrium. Okay? Now, this is, and we're going to do this in such a way that we accomplish this, we determine the fluctuations for the particles of a pair for every orientation of a pair. Okay, and what does that do? Well, the fluctuations in translation and rotation enter into the expression for the contact force. So the contact force between a pair of particles is going to be modified once we're given the form of the translational and rotational fluctuations, and then when we integrate that contact force over all possible contact orientations, we're going to get a modified expression for the stress. Okay, so that's the story. And now I'll kind of show you the calculations, although the calculations are a little painful. So, and I'm going to do this incrementally. That is for an increment of strain. I'm going to do it incrementally because when I look at increments, then the equations of force and moment equilibrium become linear, and they're easy to solve. We could do it without making this assumption, but then we'd have to deal with nonlinear algebraic equations to solve for the fluctuations. And in fact, I'm not going to take this analysis very far, but I am going to take it to the point where I can predict the shear modulus and the bulk modulus for the aggregate, and for that, let's say, near the initial state, near the initial isotropic state, and for that I only need an incremental analysis. And so that may sound trivial, but the prediction of incremental analysis is of interest, incremental moduli are of interest to people who study wave propagation in granular materials. And wave propagation in granular materials is related to subjects like prospecting for oil using sound waves moving through the earth. So there is some importance to understanding better wave propagations in granular materials. Okay, so incremental, I've got little dots over things here to denote increments. The force is related in not so simple a way as it was before. The increment in force, not so simple a way to the increment in displacement, and I'll show you in a transparency or two exactly what the structure of this tensor that I call capital KBA is in terms of the average strain and the fluctuations. And here, for some reason, I write down a discrete version of the stress that might be used in calculating the stress in a numerical simulation.
Sorry, in the previous, the summation is over n equal to 1.
The N, capital NA is the number of contacts for the sphere A, I think. And N is the number of spheres in the aggregate. Okay, so first you're integrating over the contacts of the forces, and then you do that for every particle.
You're finding the average stress in only sphere A.
You're averaging. So this gets you what's happening on sphere A, and then you average over all spheres in the.
I guess you are considering a pair A and B, and the stress in A and B may be different.
Yeah, but B here is one of the A's I'm integrating over. A is a generic indice here. And I'll use the continuum formula later. I don't know why I even wrote this down. Okay, so let's see. So now the contact displacement is more complicated. So now the contact displacement, let's say the incremental displacement of B relative to A has to do with the incremental displacements of their centers, okay, and the incremental rotation of spheres A and B. All right. And now from this, I'm going to define fluctuations. So this has an average part that's given by the affine motion, or let's say CA has an average part given by the affine motion, another part that I call capital C dot that is a fluctuation. And similarly with the angular velocities, we could decompose them into an average plus a fluctuation denoted by a capital letter. And then we'll see, in fact, that the force and moment equilibrium involve sums and differences of the fluctuations. So that's all I'm doing here, defining sums of the translational fluctuations and rotational fluctuations and differences in the translational fluctuations and rotational fluctuations. And in that case, at least in this straining where we don't have any rotations, average rotations, then I can write this displacement in terms of the average strain. So this was the average strain assumption, okay? And now this difference in the translational motions and this sum of the rotational motions is entering into the expression for the displacement of the contact. So the question is, how do we determine these guys? And we determine these guys using force and moment equilibrium, but first I have to talk about the contact. I have to talk about contact stiffness. It's all rather well. These are incremental contact stiffnesses, and they're also characterized rather well in terms of the material properties of the spheres, and they each depend, both the normal and the tangential incremental stiffness depend upon the normal displacement. Okay, but to make things simpler, I'm going to evaluate that normal displacement using the average strain. So I'm not going to allow the fluctuations to determine or to enter into the expressions for these stiffnesses. Okay, so I'm making an assumption about the contact interaction, and I'm eliminating fluctuations from the contact stiffness. That simplifies the problem.
This formula will be the same as the previous time.
But they're phrased incrementally.
Yeah.
Yeah. Okay, that's fine. So now I talk about equilibrium. So the answer to the question is, the way I'm going to determine delta dot and sigma, was it sigma dot or S dot? S dot is using force and moment equilibrium. Okay? So it's not hard to write down force and moment equilibrium. That is, we've characterized the interaction between particles A and B. The interaction between A and its other neighbors is determined in the same way, but we only use the average strain there. And similarly, particle B is interacting with A in the way I've just described, but it interacts with its neighbors according to the average strain. So this pair is in this environment that is deforming with the average strain. And what that means, so we can write down force equilibrium for particle A, that is, we sum the force between B and A and the forces between A and N, where N are all of its other neighbors. And that gives rise to an equation that involves these differences and sums and differences and fluctuations, differences and sums of the fluctuations, and other quantities, some of which characterize the way that the neighbors of A and the neighbors of B are arranged around them. Okay? So now we've got to deal with the neighborhood of individual particles. And we've got to say something about the neighborhood, or in a simplifying way, in order not to be overwhelmed by all of these neighborhoods. Okay? But in any case, these tensors, well, these two tensors in particular, are related to the geometry of the neighborhood. So this is all, let's say this is the stiffnesses of all of the neighbors of A summed up. And the stiffnesses themselves depend upon these unit vectors from the center of A to N. And similarly, this quantity that appears here depends upon the stiffnesses, and essentially the unit vectors weighted by Kn and Kt, and here a unit vector from A to N. So these guys characterize the surroundings of particle A. And there's another tensor denoted by capital A, AB, that characterize the surroundings of particle B. Okay? And G is simply a combination of components of this third rank tensor J. Okay, and I say we could do the same thing for particle B. We make use of the fact that unit vector center of A to contact B is equal and opposite to that from center of B to contact A.
So in that counting, you include B also.
Yes, included B.
You
Yeah.
include B also. So
In this expression for it.
yeah, in with the capital A.
Yes.
And why do you get a moment of the stiffness?
Say this again. Why do we get?
It's a force equilibrium. So why do you get a moment of stiffness? In J, capital J.
Let's see. Maybe if we go back to the displacement formula. Okay, so that term is probably being fed in by this guy. Okay, that is the displacement that we're interested in is the displacement of the contact. And the displacement of the contact is sensitive to the rotation of the particles. And that puts in the alternating tensor. Okay, so that's kind of an example. Oh, I see okay. So that's force equilibrium for particle A. We can write down force equilibrium for particle B. That's good. Here's moment equilibrium for particle A. That involves similar measures of the way that neighboring particles are arranged and other tensors associated with that measure. Let's see, do I define? Yeah, I define what C is. Okay, so really here's the only new measure that has been introduced by moment equilibrium. All right, so at this point, I'm going to try to simplify things. I apologize for the complexity that you've already had to endure. I'm going to focus attention now on frictionless particles. So we have no tangential resistance at all, no consideration of moment. We just focus on force equilibrium, okay? All right, and if we focus on force equilibrium, then we've got two equations, one for A, one for B, and they seem to have relatively simple structure. Apparently, we can use them to solve for this sum or this difference of the translations and this difference of the, this sum of the translations. So that's what these guys are. The difference in the fluctuations in the translation, sum of the fluctuation in the translation. So it looks like there's a hope to get a solution. But the problem is So and I guess I get it here. I invert the matrices and determine the expression for the sum of the translations and the difference of the translations in terms of the increment of average strain. Okay, so this is great. So in effect, I've done this for every sphere in the aggregate, assuming that I know something about the neighborhoods of every one of them. Okay, but I don't have that information. So now I want to make some simplifying assumption about the geometry of the neighborhoods.
So is it fair if I say the following, that you have a particle which has distribution, which is touching other particles,
Yeah,
and you deviate from your previous born assumption of average
yes,
motion by saying that one of those contacts is different and the others are the same, and the others are all moving with a fine assumption, but this one is different, and let the difference be a fluctuation, and the fluctuation will be governed by the force and moment balance.
yes.
But now you have got three variables, the sigma and the delta and the fluctuation.
What do you mean the fluctuation? Sigma and delta are fluctuations.
Delta,
Delta is the difference in the translational fluctuation.
small delta AB, that's what you don't know. You would know it if you gave
No. If I can solve for capital delta and capital sigma, I can calculate lowercase delta.
but these two depend on small, fundamentally the small delta you are trying to, if you knew that you would be done, small delta AB, because that's the one which is deviating from the affine motion. Previous one.
This line.
No, previous one. We have CI, yeah, the top line. So you have those two variables are capital C and capital omega, right? Fundamentally two unknowns.
Yeah, but right now, I'm taking as unknown this combination of those two variables.
Yes, that's,
The rotations are out of the picture.
yes, so those two combinations. So those are two unknowns.
Yes?
I was trying to say you will have to have more information because depending on these.
No, the normal displacement, that is if I knew these guys, if I knew, let's say, if I knew these guys, let's go to this expression, then I know everything, forget this. Well, let me say this, if I know only delta dot, then I have the specification for u, okay? And what you're calling lowercase delta is just the component of u along the line of centers. Okay, so I have delta, or little delta, okay? Okay, so I said these are local solutions. So I got it's great, but I don't know A and J for each particle. Okay, so now I've got to say something about those guys. Well, so maybe this is bad. So essentially what I say is, for all particles in the aggregate, that have the same orientation, I assume they have the same neighborhood. Okay? That's a sweeping assumption. But that's the assumption that we're going to make. Okay? And then I can make use of the fact that, well, I think this is true of the individual A's, but it's also true of the average. That is, we have the symmetry between the second rank tensor for A and the second rank tensor for B, and we have an anti-symmetry for the third rank tensor for A and the third rank tensor for B. And let's see, and we have a problem, if you like, because in carrying out and so I'm denoting by an overbar here the quantities that are determined by making that assumption. And if we average over these products, then we have to find a way to carry out that average.
So you're averaging by integrating over.
Well, there are two things. At first I'm assuming that the neighborhoods of all equally oriented particles are the same, and then I'm going to be integrating in order to find, let's say, so given a definite orientation, then I'm going to talk about the likelihood or how particles may be distributed about the remaining empty part of the periphery, given that there's a particle B here and the coordination number is known. Okay, so I'm going to further simplify the neighborhood of each particle by saying the average, I know particle B is in contact with particle A, and I assume I know the average number of particles per constant, average number of contacts per particle. So I'm going to assume that the neighboring particles are distributed uniformly about A. So those are the two averages that I'm going to be doing.
Because otherwise you could have any fluctuation which could be balanced by some distribution.
Yes, yeah, you're right. I mean, the distribution could play a role in the kinetics of the, yes. Okay, so now I'm beyond the individual particles, and now I'm talking about this averaged continuum in this sense. And let's see. And if I take into account these symmetry conditions in the previous solutions, then these guys cancel and these guys add. So if you've liked, I've achieved my goal in that I've got a measure at least of the difference in the fluctuations characterized in terms of this measure of the geometry of the neighbors and the average strain. So what remains is to carry out this average. And this is a mess, okay? So what I'm going to do, so if we were to take this average very seriously, there are a couple things we have to do. There's an A inverse that appears in the average. We're going to have to represent A inverse in terms of A. Well, no, we're going to have to represent the inverse of, let's see. Yeah, so this is a representation of A inverse in terms of the average and a fluctuation of A. Okay? In fact, I'm not going to bother with fluctuations of A. I'm going to evaluate this term alone and forget about these terms. So these terms are correlations between fluctuations in the neighborhood, and that's just too sophisticated. We've carried it out, but it's a mess. Okay, so the only thing I want to calculate something related to this. And I don't remember calculating A inverse, but let's see what happens. And I want to calculate that. And here's the distribution function that I use to do that. So what I'm doing is, as I said, I'm assuming that particle B is present, and I'm integrating all the rest in order to eventually have k as I integrate. And this particular formula is a little bit too complicated. So the distribution is 0 where particle B is, and then the rest of the distribution is adjusted so that there are k over 2 in the upper hemisphere and k over 2 in the lower hemisphere, but it could be made even simpler. But in any case, you can use this distribution to calculate averages of A and B. This should be approximately equal to. You can use this distribution to calculate the averages of A and B, A and J, and the coefficients then that appear in these calculations are explicit functions of the coordination number, because the coordination number is dictating the distribution. So what have we done here? Let's see. About A inverse average, and here I'm talking about A average.
A average inverse.
Pardon me?
Second line from the top,
Yeah.
you expanded and put A average inverse on the right side. You don't compute A inverse.
Okay, and I think I've made some assumption about isotropy of this guy in order to carry out the calculation, but I forget, I'm sorry. But in any case, carrying out the calculation gives us explicit expressions for these guys, or explicit expressions for the product of the averages of these guys in terms of the coefficient, in terms of the coordination number. Okay, so that gives us an expression for the incremental contact force. That gives us an expression for the incremental stress. And as I say, I've neglected correlations, so I get explicitly an expression for delta that appears here in terms of the unit vectors from the center of A to the contact, and explicit functions of coordination number. And that allows me to calculate effective moduli.
This was done using that A and B have particular orientation, right?
No, the equilibrium of force in this instance is good for every orientation.
When did you do that averaging?
When did I do what?
Because in the previous slide, this one,
This one?
no, when you assume the distribution function,
Yes.
so there was a particular orientation around which you are describing GI.
No, I mean, that's true. So if I have a pair that has this orientation, that same distribution, we use that same distribution.
That is true. So at some point in time, you have to average over all possible orientations.
I average over all possible orientations when I calculate the stress.
Right.
Yeah. So I'm calculating, so here, well, I don't show that step. Oh, yeah, here it is. So here I'm calculating all possible orientations of the modified contact force with delta determined by force equilibrium. Okay, and now let's see what that gets us. It was a struggle. So here's the expression for the shear modulus. We'll apply it to the same system I think that I had before. Realistic confining pressure, K6, which is rather high, volume fraction, 634, maybe that should be higher, and a stiffness that is appropriate for glass. So the idea here is that the average strain gave for this modulus 134, and by carrying out the simple averages that I have attempted to describe for you, we roughly cut that in half. Okay? With taking into account those correlation terms, we can do a little bit better, but we still are far from the measured value of the shear stiffness in the numerical simulations.
How strong is the answer depending on the distribution that you have seen?
Well, for example, the distribution we're using is essentially isotropic. We've got a strain in the problem that you could say should be influencing the distribution, but we're ignoring that.
I'm wondering whether at least in the disk experiments you could get a distribution, and if you use a more realistic distribution, would that answer change?
But what do you mean in the disk?
Or even from simulations you can get a distribution function, I suppose.
Well, you could do that, yeah.
If you were to use, instead of making one up, if you were to use one from an experiment or a simulation, would that answer change by much?
I'm not sure. We haven't done that because we've attempted to be as pure as possible in terms of doing the analytic. But I mean, the fair question is, what remains? You know, where could you improve this calculation?
I was thinking in terms of distribution.
Yeah, and you may be right, but
Why the same K for everyone?
Yeah.
well, K is an average.
Yeah.
Yeah. No. So that, I mean,
Too in some sense, right?
yeah. So you're right. That I would suspect that is a graver assumption than the distribution. That is assuming that every particle has the same number of contacts, because the K enters the theory in a rather strong way. Okay? So, so you say, well, what do you do? Well, you suppose that K has an average and a fluctuation. Yeah. And then try to model the fluctuation.
For that you will need a more global balance of it.
Well, so how did we come up with distributions? We just made the simplest possible assumption. So, I mean, you can, I don't know exactly what a simple assumption would be to govern K, but
No, I mean, if you're going to solve the fluctuation in K from a balance, yeah, then you will,
pardon me, if you're going,
if you, just like you solve the fluctuations of one contact from the moment and force balance of the particle, if you're going to look at fluctuations, you will need another equation, right?
yeah, but I don't know what equation I have. I mean, that is, it would be, so people talk about evolution equations for fabric. And if you represent K as a second-rank tensor, then, represent the fabric as a second-rank tensor, then K is related to the trace of that. So, yes, if you're going to talk about,
Yes, it may not be an isotropic K that's going to get you there as well, perhaps.
yeah, so
Yeah.
what do you mean by an anisotropic K?
Well, the tensor or K in some sense.
Well, I would say maybe K is influenced by the existing strain, and that would give you an anisotropic distribution of K.
It's a long way to go. 8 and 41 is pretty drastic.
Okay,
But
well,
have people done the lattice model, and your calculation should be exact for that, I presume, right?
with the lattice model, you mean periodic lattice.
Yeah, right.
The average strain is exact.
Yeah, right. So you should be exact, right?
Yeah.
So people have predicted then the modulus is for the lattice, and you're telling me it's 8 to 134. That's huge.
Yes,
Yeah.
yeah.
I think right. It is huge. Right.
Yeah, I mean, this is clearly wrong.
No, but then it also tells you a lattice versus a disordered medium, right?
Yes,
Is a huge difference.
yes,
I mean,
Yes. Well, you're saying that not everyone knows that. I mean,
But it's huge, there it is.
yeah. Well, that might keep us in business.
Yeah.
Okay, thanks a lot. I hope I didn't cause you too much pain.